Alright, so now what we're going to start talking about is what we call statistical error and statistical power. So here's what we got here. The null, this blue region right here is our hypothesized distribution. So in this case, we hypothesize that the mean is 100. The pink distribution represents what the actual distribution is. So right now the actual distribution would be mu is 1/3. Alright, but what we're going to talk about first is what we call a type 1 situation. In a type 1 situation, the null hypothesis is correct. So in this case, we would have the null hypothesis would be that mu is 100, let's say, and we'd be testing, is there evidence that mu is greater than 100? Okay. So in this case, the null hypothesis is correct. And our sampling distribution would match this distribution right here. So in this case, this right here is called alpha. Alpha is 0.05, and that represents this dotted line. And that alpha is 0.05 means that in a one-tailed test, this blue region is 5%. And basically what we talked about is when we do a hypothesis test and we have a 5% level of significance, or alpha level, we also call that the level of significance. Any big p-value that we get that's under 0.05, we would reject the null. So if we were to do random samples, okay, based upon this distribution, then 95% of those samples would wind up in the red region, and those are to the left of 0.05, and that means that their p-value is above 0.05, and we would not reject the null, which is good. We don't want to reject the null here because the null hypothesis is true. Okay. Now you may be asking, you might be saying, well, hold on, Mr. O'Neill, you can never say that the null hypothesis is true. I said when you do a hypothesis test, you can never say that the null hypothesis is true. However, in reality, the null hypothesis may be true. Okay, so in this case, we know that the null hypothesis is true. We're not writing the conclusion of a hypothesis test. We just know that as a fact. Okay. Now, we could get a sample in the blue region, however, we're not going to get a lot of them. Okay, as a matter of fact, that blue region is 5%. So, what that means is, if we got a sample that wound up in that blue region, then we would reject the null. Well, that's not a good thing, because in this case, we hypothesized that mu is 100, and mu actually is 100. Okay, and we tested it that mu is greater than 100 because our test is to the right here, so that means we're doing a one tail, what we call an upper tail test, which means we're testing that it's greater than. Okay, so if we wind up with a sample in that blue region, we would wind up making an error, and that's called a type 1 error. Type 1 error is when the null hypothesis is true and we wind up rejecting it. Okay, in a court of law, that's like having an innocent defendant that we find guilty. Okay, so there are people who walk into court who are innocent who wind up getting convicted. Okay, that's not a good thing, but it does happen. And the same thing in hypothesis testing. We do all the right things, but we get a sample in this blue region and we wind up rejecting the null when in fact the null hypothesis is true. So that's what we're going to talk about in the first part of this chapter, is what we call type 1 error. Okay, so now we're talking about the innocent defendant. And what that means, the innocent defendant, means that the null hypothesis H of O is true. So we got our hypothesized p-value in this distribution and the actual p-value. So what happens here is our hypothesis is correct. So if we have the null hypothesis that p equals 0.7 and the alternative hypothesis that p is greater than 0.7, then this is true. Okay. So in this scenario, H of O is true. However, there is a chance that our defendant will be found guilty. Okay. So we got an alpha level here, and it says we're going to reject, we call that 0.05 level that we're going to reject that alpha. We also call that the significance level. And remember, the significant level is we're looking for a p-value when we do our hypothesis test that's below 0.05 to reject a null. Well, what is the probability that we will get a p-value that's in this region right here? This is the actual distribution. So what is that probability that we get a p-value in this region? Well, it's your alpha level. It's 0.05. Okay, 5% of our samples from this distribution, this actual distribution, will give us p-values that are in this rejection region. So we would have a p-value in this region that's less than 0.05, and we would reject the null, and we would accept the alternative. Well, that's not good, okay, because our null hypothesis happens to be true here. Okay, so we don't want to reject the null here. Okay, so if we reject at the 0.05 level and the distribution for the null is correct, then there is a 5% chance that we will obtain a sample in a rejection region. Now, if I made my alpha level smaller, let's say I made my alpha level 0.01, well, what would that do to the line? Alpha level of 0.01 would make this region smaller. So this would be an alpha of 0.01. So now what happened? Well, this region over here, there's only 1% as opposed to 5%. So when we lower our alpha level, we lower our type 1 error. Okay. Now the question I ask here, what happens if we rejected the 0.1 level? Well, the 0.1 level would be to the left. So I'm going to make that a really dark line. So that's alpha equals 0.10, and that would be this entire region right here. Well, that's 10%. That's 10% of this distribution. So the chance that I would get a p-value that ends up in this big rejection region is now 10%. So what happened? Well, we increased alpha from 0.05 to 0.10, so type 1 error increased. So the probability of making this error is equal to the level we reject at, or what we call alpha. This is called type 1 error. So type 1 error, you got to get this in your mind. H of O is true, but we mistakenly reject. So H of O is true. You know, if you made an error, you made a mistake. So H of O is true and we made a mistake. This is the same scenario as finding an innocent defendant guilty. Okay? Same thing as finding an innocent defendant guilty. Alright, so what we have here is, yeah, that's pretty good. Okay, so here's what we got. We hypothesized that the mean is 100. Okay, that's this right here. But the actual mean is 121. Okay. So in this case, our null hypothesis is false. Okay. Now, the dotted line here right here is still alpha. Okay, that's right here. This is this 0.05 level. Okay, so hypothesized distribution in blue, actual distribution in red. Again, we're doing an upper tail test, so our alternative hypothesis here would be that mu is greater than 100. So we are going to reject anything that we get, any p-value that we get that's to the right of the red dotted line. Okay, so when we sample, the results that we're going to get are going to be from the pink distribution, because that's where the actual distribution lies. Okay, so we have a bunch of players in here. Okay, so we can get from over here all the way over here, but we're only going to reject the null, which would be a good thing here because the null is false and the alternative is true. Anything that comes, any p-value that's to the right of our red dotted line. Well, where is that represented here? Well, that's represented from here all the way over to here. So this pink region here and this little blue region down here, that's all part of this. That means that we wound up drawing a sample that wound up being in the rejection region. Well, that's good, because in this case we hypothesized that mu is 100 and mu is actually 121. So that's a good thing. Okay. So what we call that in this region over here is we call that power. Okay, that's called power. Now there is a chance, hold on, I just shifted my, there we go. I just shifted my distribution. Okay, so there is a chance that we could get a sample in this part right here. That would be this red region. That red region is called type 2 error. So we got a p-value that's more than 0.05. So we said, okay, we fail to reject the null. We don't reject the null when the null is false. Okay. We also call that beta. Okay, beta. See this right here? That's beta. And this down here is power. Now if you look at in our distribution here, what to the red region plus this pink region, and this little blue region is part of the pink region, what did they add up to? Well, they add up to 100%. Okay, so what does that mean? Well, power is the probability that we make the correct decision when the null hypothesis is false. So in this case it's 0.876. Beta is the probability that we make the wrong decision when the null hypothesis is false. Well, that's 0.124. Well, if you add those two together, what do you wind up with? You wind up with 100%. So basically what we're saying is the probability of making the wrong decision plus the probability of making the right decision add up to 100%. Okay. Okay, so the players that we have in the game right now is, yeah, power. Power's good. In this case, we reject the null when the null is false. Beta, type 2 error. That's the probability of failing to reject the null when the null is false. And we got alpha, and that's our rejection level, or what we call our significance level. Okay. So there are a few things that could affect our type 2 situation, or our type 2 error situation. Okay. In this case, our sample size was 4. Okay. So we're going to take larger samples. Okay. So now what we're going to do is we're going to take sample sizes of 10. And what that's going to do, there's 121. There it is. What did that do to power? Well, that increased power. Okay, this region now is 99.7%. There's only a little tail over there. So what do we do when we increased our sample size? What is that doing? Well, we got more evidence. Every one of our samples, when we take a sample, we now have more evidence. Okay? So if we have more evidence, we're more likely to make the right decision. So let me see if this will, okay, 121 again. So did you also see what happened to the distribution here? Okay, watch these two distributions when I increase sample size. What did they do? I go from 4 to 10. There's 4. There's 10. What happened? Well, if you said that the two distributions got narrower, you're right. So what does it mean when the distributions get narrower? Well, what it means is there's less variation. So sample size and variation have an inverse relationship. When you increase sample size, you reduce variation. Well, we already determined when we increase sample size, we increase power. So that must mean when we reduce variation, think of it this way. Variation is about your evidence all telling the same story. So when you go into a court of law, if there's a lot of variation in your testimony against the defendant, then you're less likely to convict the defendant. However, if all of your witnesses line up and all tell the same story, hence less variation, more consistency, then you're more likely to convict a guilty defendant. Okay? So that's two things that contribute to power. Okay? So the first thing was sample size. When sample size goes up, power goes up. When variation goes down, power goes up. Okay? The second thing we're going to look at is this line here. I'm going to change my alpha level from 0.05 to 0.01. So let's watch this region here. Now remember, power was 0.876 and beta was 0.124. Well, what happened to power? Well, what we did is we reduced power. The type 2 error, this red region, got bigger, and our pink region, which was our good thing, that wound up getting smaller. What did we do to the line? Well, let's watch the line. 0.05. See, the line went left. Now we go to 0.01. Line goes right. The distributions didn't change. So what does the line represent? The alpha level represents your significance level. And in order to reject the null, you have to have a p-value that's under your significance level. So if I set my alpha level at 0.05 and I do my hypothesis test and I get a big p-value of 0.03, then I would reject the null. That's good here because the null happens to be false. The alternative is true. However, if I set my alpha level or my significance level at 0.01 and I get a p-value of 0.03, I don't reject the null unless my p-value is less than my significance level. So if I get a big p-value of 0.03 here, I fail to reject the null. Hence, I make a type 2 error. So when you reduce your alpha level or your significance level, it's harder to reject the null because you got to get a p-value that's under that to reject it. Okay? So what would happen if I made my alpha level 0.10 instead of 0.01? Well, we started out with let's see. Let me change this to 121. We started out with 0.876. We went to 0.01. Now we're going to go to 0.10. So now what's that going to do to the red line? Well, it's going to move it to the left. We went from 0.876 here to 0.936. So power went up. Why? Because it's easier to reject the null. If I get a big p-value of 0.07, I would reject it to 0.10 level, but I wouldn't reject it to 0.05 level, and I wouldn't reject it to 0.01 level. So my power is higher the higher my alpha level is, because I want to reject the null. Okay, in this case the null hypothesis is false, so I want to wind up rejecting it. Okay. Okay, so the last thing let's look at, there's one more piece that we got to look at, and that is how far is the actual distribution from the hypothesized distribution. So in this case we hypothesized that mu is 100, but mu is actually 121. It's pretty far away, so hence we have a pretty powerful situation. Okay, the power here is high. But let's say that we hypothesize that mu is 100 and mu is actually 101. It would look like that. Well, do we have a real powerful situation? Well, no, because our hypothesized mu is not that far from where mu actually is, so this is going to be pretty hard to detect. Okay? So when our hypothesized level and our actual level are very close, okay, then it's hard to detect a significant difference. So hence in this situation it's going to be hard, it would be hard for us to detect that mu is above 100, and probably it'd be very unlikely. As a matter of fact, there's only a 0.065 chance. There's a 93.5% chance that we'd make a type 2 error. But as I increase, let's go from 101 to 110, now my power went up. Okay, now the actual distribution is farther from the hypothesized distribution. So the likelihood that I'll detect it is increasing. And then if I go up to 120, then I get into a pretty powerful situation. That's 0.847. If I probably went to 125, yeah, I mean that the hypothesized distribution and the actual distribution are far apart now, so it's going to be pretty easy to detect it. Okay, so you basically got four variables that influence power. N is your sample size. As sample size increases, power increases because you have more evidence. Okay, alpha, as alpha increases, well, this red line, when you increase alpha, you move the red line to the left. Hence, that makes this red region smaller, that's type 2 error, and it makes this pink region larger. Power goes up. So when alpha goes up, power goes up. Okay, what I call effect size, and that is the difference between these two distributions. When they're fairly close, the likelihood that you're not going to reject the null when the null is false is highly likely. When they're far apart, then it's going to be easier to detect the difference in your hypothesis test. And the one that has an inverse relationship is variation. So if we increase sample size, we reduce variation. And when we reduce variation, we increase power. Here, power is 100%. Type 2 error is 0. Okay? So that's what we're going to talk about next in our notes. Alright, so let's look at this now. So now we got the guilty defendant. So in this case, we hypothesize that P is 0.7 and The alternative is that P is greater than 0.7. So we hypothesize that P is 0.7, but P is actually way over here. P is like 0.85. So our H of O is false. But what's going to happen? Well, this person is going to be found not guilty. They will not be found innocent because they still must go through the trial. Okay? So, we got an alpha level. Here's what we hypothesize it to be. We would reject any p-value that winds up to the right of alpha, because that means it would be less than our level of significance. Well, when we draw our samples are actually going to come from this distribution. So this region over here is called the power region. And power is the probability of correctly rejecting H of O when H of O is false. So that's a good thing. However, we could wind up with a sample that falls in this region. And we call that region beta. And beta is the probability of incorrectly failing to reject H of O when H of O is false. By the way, beta is also called type 2 error. Okay. Well, you got to make a distinction right now. If we're dealing with type 1 error, then the null hypothesis is true. When we're dealing with type 2 error, the null hypothesis is false. Okay? So, right now, our actual distribution is different than our hypothesized distribution. So the null hypothesis is false. Alpha is our significance level. That we will reject H of O if the p-value is less than this level. So if we say our alpha level is 0.05, any p-value that we get that's less than 0.05 means that we would reject the null and accept the alternative. Okay? So that's an overview of a power in a type 2 situation. Okay? Alright, so we talked about the 4 factors. So if you go in a court of law, what are the factors to defend to convict a guilty defendant? Well, number 1 is the amount of evidence. More evidence means a more likely conviction of the guilty defendant. Okay. The second thing is consistency of witness testimony. The more consistent the testimonies means a more likely conviction of the defendant. So if all of your witnesses go in and tell the same story, then the defendant is likely to get convicted. Thirdly is the seriousness of the crime. The more serious the crime, the more likely a guilty defendant will be convicted. And fourthly is the judge. A judge that requires an easier burden of proof means a more likely conviction of a guilty defendant. Okay? So, those are four variables that when you go into a court of law, okay, and the defendant is guilty, those are four variables that go, that contribute into correctly determining that the defendant is guilty and convicting that defendant. Alright, so we're going to talk about two of these variables right now, the amount of evidence and the consistency of the testimony in terms of a hypothesis test. More evidence means a larger sample size, larger n size. What does sample size do to variation? Larger samples reduce variation. Okay, so if you notice here, the hypothesized P and the actual P are the same distance away. Okay, so if I draw my alpha level at the, let's say the 0.05 level, that's alpha, then this would be beta and this would be power. But now if I take a larger sample size, what a larger sample size is going to do is it's going to make my distributions narrower. Hence it's going to reduce variation. So now when I do this, look what happened. Beta decreased, power increased. So sample size and variation kind of go together. Okay, so if you increase sample size, you reduce variation. A hypothesis test with a larger sample has more power. This is the larger sample. How do I know? Because it's narrower. A hypothesis test that has a sample with less variation has more power. This has more variation, this has less variation. Okay, this has a greater proportion, greater percentage of this distribution is in the power region than this distribution right there. Alright, the seriousness of the crime. The more serious the crime, the easier to convict. Okay. Felonies are more likely to be convicted than misdemeanors. Right. A person who robs a bank is more likely to be convicted than a person who runs a red light. Okay. So in this case we have an actual value that is far away, that is farther away from the hypothesized value. It is easier to reject H of O and accept the alternative. Okay, so again, here you see that the actual is closer. So if I take an alpha level of like right there, then this is beta, this is power. But if I take that same alpha level over here, now that the actual is farther away from the hypothesized, then this is power and this is beta. Okay. So the farther actual P or mu, could be mu if we're dealing with means, is from the hypothesized P or mu, the more power the hypothesis test has. So the more significantly different it is, then the more likely you are to reject the null and accept the alternative. Okay, so let's now look at the judge. What does the judge do in the case? Well, the judge is the factor in the courtroom that sets the burden of proof required to convict the defendant. So the judge in our hypothesis test is alpha. So if we set our alpha level, let's say we set our alpha level at 0.05. That's our level of significance. Well, this is beta. This is power. Now we set our alpha level at 0.01. Now the distributions are the same distance apart. Okay, so we haven't changed the distributions, the relationship. So the only thing that we're changing is alpha. So now we do alpha is 0.01. Well, now this is power, and this is beta. Okay. So what happened? Well, power decreased when you went from a larger alpha to a smaller alpha. Why is that? Because remember, in order to reject the null, hence find the defendant guilty, you got to get a p-value that's below whatever your alpha level is. Well, it's more likely to get a p-value below 0.05 than it is to get one below 0.01. Okay, so the larger the alpha level, the more power the hypothesis test has. It has a direct relationship. Okay, so making a alpha level larger, what that does is it moves the line to the left. So you move the line from 0.01 way over here, and you took it and you moved it left. Hence your power got larger and your beta got smaller. So the conclusion is we can reject the null hypothesis when in fact it is true. This is called type 1 error. When a null is true and we reject it, type 1 error. We can fail to reject the null when in fact the null is false. This is called type 2 error. So here we have a little chart. So in our chart, we know that H of O is true, and we know that H of O is false. And we reject H of O. And here we fail to reject. Okay. So if we reject H of O when H of O is true, then we committed a type 1 error. Okay, so that is this situation right here. That's the situation. We hypothesized right there. We hypothesized the distribution. This is the actual distribution. We set the alpha level, and anything to the right of alpha, we wound up rejecting the null. So in effect, what is the probability of committing a type 1 error? It's alpha. It's our significance level. If H of O is true and we fail to reject H of O, we made the correct decision. Good for us. And now, when we reject H of O when H of O is false, that's good. So when we're dealing with type 2 error, that's the situation right here. Okay, so when our null hypothesis is false and we reject it, we wind up in this region. Well, what is this region? Well, that region's power. Well, what does it equal? Well, we know that power plus beta is 100%. So the probability of that is 1 minus beta. And then if we fail to reject the null when the null is false, we commit a type 2 error. Probability of that is beta. By the way, 1 minus beta equals power. So type 1 error, probability of making a type 1 error is alpha. As alpha increases, type 1 error increases. Type 2 error, the probability of making a type 2 error is beta. Probability of correctly rejecting H of O when H of O is false is power, which equals 1 minus beta. And we talked about power also increases as alpha increases. Okay? Alright, so let's look at problem 1 here. Currently 40% of all juniors in schools score more than 1,000 on the SATs. That's math and verbal combined. A new SAT prep program is to be piloted this year with a random sample of 50 juniors that will take the SAT in November. You will run a test and reject it at the 0.05 level. So what is our hypothesis here? Well, in this case, this 1,000 here, that's a mean, that's mu. So our null hypothesis is that mu equals 1,000. Now what do we want to happen to 1,000 from taking the SAT prep course? Well, we hope it increases. We hope to see that the mean will increase in our sample. That means that our course was effective. So if we fail to reject H of O after we run the hypothesis test, so after we do the SAT prep course and we run the hypothesis test, we wind up with the null hypothesis that mu equals 1,000. That's what the evidence shows. So if we fail to reject H of O and we don't have evidence to reject this, what does that mean? Well, it means that we don't have evidence that the course worked. Okay? So this means we have no evidence that the course worked. Now, if we reject H of O, then we would wind up with this conclusion. We would wind up at the alternative hypothesis. Well, if that's what the evidence shows, then what does that mean? Well, we have evidence that the mean is greater than 1,000. So that means we have evidence that the course increased mean SAT test scores. So what is type 1 error in this problem situation? Well, here's what we got. So what does type 1 error mean? Type 1 error means that H of O is true. Now we're talking about H of O is true after we've done the hypothesis test. Okay? Well, if H of O is true, if mu is 1,000, then we have this situation. Okay, so in fact, the course did not work because the mean is still 1,000. Well, we made an error. What did we do? Well, we rejected the null, okay, when in fact the null is true. So we accepted the alternative. So what did we do? We made an error. Okay. We found evidence that the course worked when in fact it was ineffective. Okay? Okay, so what happens when we increase alpha in a type 1 situation? Well, remember, this is our hypothesized mean and our actual mean. So this is our actual mean. So we increase alpha. There's alpha equals 0.05, and we increase it to 0.10. Well, what does alpha represent? It represents our significance level, and if we get a p-value that's to the right of this line, then we would reject the null. Well, we don't want to reject the null because, in fact, in a type 1 situation, our null hypothesis is true. So what do you do with this region right here when you go from the solid line to the dotted line? Well, you increase the rejection region, and that's not a good thing. So what do? In fact, when you increase alpha from 0.05 to 0.10, you increase the likelihood of committing a type 1 error by 5%, by 0.05. Yeah, so you increase the likelihood of making a type 1 error by 0.05. So what's a type 2 error in this situation? Okay, now we got to shift gears. Null hypothesis, use 1,000. Alternative hypothesis, mu is greater than 1,000. What's true in a type 2 situation? This is false, this is true. It's like the exact reverse. The null hypothesis is false. So, if this is true, what does that mean? Well, it means that, in fact, the new mean is greater than 1,000. But we made an error, so what do? We fail to reject the null. So, type 2 error means that the course was effective, but we do not have evidence that shows this. That's what it means in context. So what it means is we didn't reject the null when in fact the null was false and the alternative was true. So in fact we should have rejected the null and we should have found that the course was effective, but we didn't. Okay, so let's say that our hypothesis is that mu is 1,000, but mu is now 1,100. Okay, and here's our alpha level, and this is beta, and this is power. So what is beta? Well, beta is the probability of making a type 2 error. So it's the probability of failing to detect that the course was effective when in fact the course was effective. So we failed to find that the course was effective when in fact the course worked. That's type 2 error in this situation. What's power in this situation? Well, power is the exact reverse. That means we wound up in this region here. That's a good thing. It's the probability of correctly determining that the course was effective. Okay. So that's good. We want to determine that the course was effective because this is true, right? The mean is now greater than 1,000. Okay. Now here's what I want you to remember here. We talked about 4 variables. Okay. Its effect on power. Okay, when sample size on power. Okay, and then remember, sample size has a direct relationship with power. So when sample size goes up, power goes up. When sample size goes down, power goes down. Alpha has a direct relationship with power. So when alpha goes up, power goes up because the line shifts to the left. That's a good thing. Okay. Effect size, the farther the distributions are from each other, has a direct relationship. The farther they are away, the more power you're going to have. The more significant the difference is, the more likely you are to reject the null. The only one that has an inverse relationship is variation. When variation increases, this one is indirect, then power goes down. Okay. So those are the effects on power, and then the effect on beta would be the exact opposite. So sample size, I always remember these. I just know there's 3 that have a direct relationship with power, and then I always know that if something, if sample size goes up, power goes up. Well, if power goes up, beta goes down. If alpha goes down, then power goes down. If power goes down, then beta has to go up. If effect size goes up, power goes up, beta goes down. If variation increases, this one's indirect, variation increases, power decreases. Power decreases, beta must increase. Okay? So I just remember this right here. I don't go into, I know that then it had the exact opposite effect on beta. So we're going to decrease our sample size. So if I decrease sample size has a direct relationship with power. Power goes down. Beta, probability of making type 2 error, goes up. Increasing alpha. Alpha has a direct relationship. Power goes up. Beta goes down. Changing the sample from a heterogeneous group to a homogeneous group. Okay, well, what does heterogeneous mean? Heterogeneous means we have a lot of different types of subjects in the group. Homogeneous means we have a lot of the same type of subjects in the group. Homogeneity is sameness. So what do? If we go from heterogeneous to homogeneous, we reduced variation. So I know that variation has an inverse relationship with power. So if variation goes down, power goes up, beta must go down. And I think that's going to conclude our notes for now for chapter 21.